Now we should be ready to answer the questions about humidity. We'll start with the question, what does it mean when the dew point temperature goes up? We'll start by looking at these two bottles of Coca-Cola. If I were to ask you which of these is more full, the answer you gave me would depend on how you thought about it. If I answer the question based on what percent full they were, well, we would say they're both 100% full. They're brand new bottles of Coca-Cola. But if you were to answer the question based off of which one contains more liquid, well, clearly the 2-liter bottle contains more liquid than the half-liter bottle. The same concept applies when we talk about dew point temperature. We said before that cooler air can hold less moisture. The warmer air can hold more moisture. If we apply this concept to dew point, we can look and see. So at a 10 degrees Celsius, let's say that this beaker right here represents how much water the air could hold. As we get to higher and higher temperatures, the size of the beaker increases because the more water that the air could hold at that temperature. We notice in this example right here at 15 degrees Celsius, this beaker is completely full. It's 100% full. Whenever we have the relative humidity just reaches 100%, we call that the dew point. So the dew point in this situation is 15 degrees Celsius. If we look in this example, 28 degrees Celsius is completely full. Now both are 100% full, but which one contains more moisture, contains more water? Clearly, the 28 degrees Celsius, which is at its dew point, contains more water. So a dew point of 28 degrees Celsius as opposed to 15 degrees Celsius would contain more moisture and would have the capacity for more humidity. The relative humidity would be 100% in both cases, but there would be more moisture in the air. Why was the relative humidity outside more than the relative humidity inside? As somebody who lives in Houston, Texas, we should understand this one pretty well. There's something that we have in our house that helps to keep the humidity down. And when that goes out in the summer and we have power outages, we get pretty upset about it. Think really long and hard about what it is that we have attached to our house that will help to keep the relative humidity down inside. Let's move on to the next question. What would happen in this lab if the relative humidity were 0%? So think about what that really means. If the relative humidity were 0%, that means that there would be no water. There's no water in the air at all. So when we put ice into our beaker of water and we stirred, we've been waiting for the water that's in the air to condense on the outside of that beaker. If there were no water at all in the air, how much ice would we have to add to get water to condense on the side of the beaker? Well, remember, there's no water there at all. Let's think about the opposite situation. What if the relative humidity were 100%? The air was completely saturated, full of water. Okay, this is a situation that we see in rainforests. How much ice would we have to add before dew started to form, before we started getting condensation to form? If the air was already completely full, wouldn't dew already be forming? We would barely have to add any ice at all. And finally, we want to know which of the three methods that we use to calculate relative humidity is the most accurate. Three methods we used water and ice in the beaker. We kept adding ice until we started to see dew form, or condensation form on the outside. We used the sling psychrometer, where we dipped the wet bulb into water, spun them around, and then compared the dry bulb and the wet bulb temperature. And then we used the GLX probes. Now, one is clearly more accurate. The more challenging question is, what made the other ones less accurate? Now, no matter how hard we tried, or no matter what good scientists we were, there were things that were just difficult about using those tools that made them less accurate. With the water and ice, as we added ice and we started to notice condensation form, how easy was it to notice when the condensation started to form? Did you notice the very first second there was a little bit, or maybe was it there for a few degrees more? If you added a lot of ice, Did the temperature drop more quickly? And maybe by the time that you noticed condensation, the temperature had already fallen. And with the sling psychrometers, especially the sling psychrometers that we used in our class, how easy was it to read the temperature on them? Did each thermometer even agree when they weren't dipped in the water, when they were just out in the room temperature? Okay, those kinds of things should make you think about what possibly could make there be some inaccuracies in our tools. Through no fault of your own, those tools were less accurate.